Have you ever pondered the possibility of the future impacting the present? Could the events that haven't happened yet shape what's happening right now? Imagine if events that haven't happened yet could affect what's happening right now. It's a concept that challenges our understanding of time and the very nature of causality. But what if it's not just an abstract idea, but a reality that's governed by the laws of physics? Today, we'll explore the fascinating concept of how the future can impact the present, and how the laws of physics play a crucial role in understanding this mind-bending idea. We'll delve into the worlds of relativity, string theory, quantum mechanics, and field theory, and learn about the formulas and theories that allow us to comprehend how events that haven't happened yet can shape the present. We'll take a journey into the minds of brilliant physicists who have made groundbreaking discoveries that have challenged our traditional view of the world. We'll explore the principles of reverse causality and closed time-like curves, and learn about how they provide new insights into how the future can impact the present. Step into the unknown, where the mysteries of time unfold. I am the timekeeper, and this is 2D time. The laws of relativity tell us that time is relative and can be affected by the observer's velocity and gravitational field. As we approach the speed of light, time slows down, and events that appear simultaneous to one observer may not be to another. This means that the future can impact the present, as an observer moving at high speed may experience time differently than someone at rest. For example, the twin paradox illustrates how time dilation can cause one twin to age slower than the other twin, depending on their relative velocity. This means that from the perspective of one twin, the other twin has experienced less time, which creates the possibility of one twin being able to travel to the future and return to the present, while the other twin has aged normally. However, the concept of causality is limited by the boundaries of the light cone, which separates events that can affect each other from those that cannot. Anything inside the light cone can affect an event, while anything outside cannot. The light cone divides events into past, present, and future, and it's the same for all observers. This means that if we go back in time and change the past, we create the possibility of paradoxes, like the grandfather paradox, where a time traveler kills their own grandfather before their parent is born, which creates a paradox that cannot be resolved. This means that causality must remain consistent with the present and future, and any attempt to change the past must be prevented. One possible solution to this problem is the idea of reverse causality, where events in the future can affect events in the present. This idea is based on the concept of closed time-like curves, which are paths in space-time that loop back on themselves, creating a Mobius strip-like shape. This allows the future to interact with the past, but it also raises questions of consistency and paradoxes. The Einstein field equation is a fundamental equation in the theory of general relativity, which relates the curvature of space-time to the distribution of matter and energy in the universe. The equation is written as r mu nu minus half of r times g mu nu plus lambda times g mu nu equals 8 pi g over c to the 4 times t mu nu, where r mu nu is the Ricci tensor, r is the scalar curvature, g mu nu is the metric tensor, and t mu nu is the stress energy tensor. The left-hand side of the equation represents the curvature of space-time, which is created by the presence of matter and energy. The Ricci tensor and scalar curvature describe the curvature of space-time, while the metric tensor describes the geometry of space-time. The right-hand side of the equation represents the distribution of matter and energy in the universe, including mass, energy, and pressure. The equation essentially tells us that matter and energy create the curvature of space-time, which affects the motion of objects and the passage of time. The equation is often used to make predictions about the behavior of objects in the presence of massive bodies, such as planets and black holes. It also plays a key role in our understanding of the universe on a large scale, including the expansion of the universe and the formation of galaxies. The Einstein field equation is a powerful tool for understanding the relationship between matter, energy, and space-time. It is a fundamental equation in the theory of general relativity, and provides a key foundation for understanding the nature of the universe. The geodesic equation is a fundamental equation in the theory of general relativity that describes the motion of objects in curved spacetime. The equation is based on the principle that objects in free fall move along the shortest path, or geodesic in spacetime. In curved spacetime, this path is not straight, but instead follows the curvature of spacetime. Imagine rolling a ball along the surface of a curved sheet. The ball will follow the shortest path on the sheet, which is a curve that follows the curvature of the sheet. This is similar to how objects move in curved spacetime, where the shortest path is along the curvature of spacetime. This means that the future can impact the present, as the motion of an object is affected by the curvature of spacetime. In a universe where time is curved, an object moving along a geodesic path can experience time differently than someone at rest, creating the possibility of the future impacting the present. The geodesic equation is a fundamental equation in the theory of general relativity that describes the motion of objects in curved spacetime. The equation is based on the principle that objects in free fall move along the shortest path, or geodesic in spacetime. In curved spacetime, this path is not straight, but instead follows the curvature of spacetime. The equation is given by d square x to the over dx square plus gamma of bc times dx to the b over ds times dx to the c over ds equals 0, where x to the a is the position of the object in spacetime, s is the proper time of the object, and gamma of bc are the Christoffel symbols of the second kind, which describe the curvature of spacetime. Let's break down the different elements in the equation. d square x to the a over dx square represents the acceleration of an object in spacetime. It's the second derivative of the object's position with respect to its proper time, which is the time experienced by an observer traveling along with the object. The Christoffel symbols, denoted by gamma, describe the curvature of spacetime and are used to define the connection, which represents the way that tangent vectors to spacetime are parallel transported along a given curve. The Christoffel symbols are also used to describe the effect of gravity on the motion of an object in spacetime. dx to the b over ds times dx to the c over ds represent the velocity of the object in spacetime. They are the derivatives of the object's position with respect to its proper time. The indices of b and c represent the coordinates of spacetime, where 0 represents time and 1, 2, and 3 represent space. The equation is equal to 0, which means that the object is moving along a geodesic, or the shortest path through spacetime. This equation is used to describe how an object moves in curved spacetime, taking into account the curvature of spacetime and the motion of the object. This equation is important for understanding the relationship between the future and the present, as it allows us to predict the motion of objects in the presence of massive bodies, such as planets and black holes. In a universe where time is curved, the motion of objects can be affected by the curvature of spacetime, creating the possibility of the future impacting the present. One example of a solution to the geodesic equation is the Gödel solution, which describes a rotating universe that allows for time travel. In this solution, the universe is expanding and rotating, and the motion of objects is influenced by the rotation. The result is that closed time-like curves are possible, which means that time travel is possible. This creates the possibility of the future impacting the present, and the present impacting the past. The geodesic equation is a powerful tool for understanding the motion of objects in curved spacetime, and the Gödel solution is an example of how the principles of general relativity can allow for the future to impact the present. These concepts provide a fascinating and complex view of the nature of time and the universe, and they continue to challenge our understanding of the world around us. By understanding the mathematics of space-time curvature, we can better understand the relationship between the future and the present, and how they can impact each other. The geodesic equation is a key equation in the theory of general relativity, and it provides a powerful tool for understanding the motion of objects in the universe. Enter string theory, a candidate for a theory of everything that unifies gravity. String theory is a theoretical framework that attempts to unify all the fundamental forces and particles of nature into a single coherent framework. It proposes that the fundamental building blocks of the universe are not particles, but tiny one-dimensional strings that vibrate at different frequencies. String theory has the potential to explain some of the most fundamental questions in physics, including the nature of gravity, the unification of forces, and the origin of the universe. One of the most fascinating concepts in string theory is the idea that the universe may have extra dimensions beyond the 4 dimensions we experience in everyday life. In fact, the mathematics of string theory requires the existence of 10 or 11 dimensions, depending on the version of the theory. But how does all of this relate to the possibility of the future impacting the past? One way that string theory allows for this idea is through the concept of closed time-like curves, which are paths through space-time that allow for the possibility of time travel. The idea is that if the universe has extra dimensions, it's possible that some of these dimensions are curved in such a way that they create closed time-like curves. In these curves, an object could travel back in time and interact with itself in the past. But how does string theory allow for the possibility of closed time-like curves? One theory is that the extra dimensions of space-time could be compactified in such a way that they form a shape called a Calabi-Yau manifold. The Calabi-Yau manifold is a mathematical shape that has 6 dimensions that are curled up into a tiny space. The strings in string theory can vibrate in these extra dimensions, and the way they vibrate determines the properties of the particles and forces we see in the universe. But the shape of the Calabi-Yau manifold can also affect the behavior of closed time-like curves. So, in a sense, the mathematics of string theory could allow for the possibility of closed time-like curves, and thus the possibility of the future impacting the past. However, it's important to note that the existence of closed time-like curves is still a theoretical concept and has not been experimentally proven. Despite this, the idea of closed time-like curves has captured the imaginations of scientists and science fiction writers alike, and it remains a topic of intense research and debate in the field of theoretical physics. Whether or not closed time-like curves exist in the universe, the study of string theory has opened up new avenues of research into the fundamental nature of the universe, and the potential for new discoveries that could revolutionize our understanding of the world. Finally, let's look at quantum mechanics, which tells us that particles can be in multiple states at the same time, and that measurements can affect the outcome. This leads to the famous thought experiment of Schrödinger's cat, where a cat in a box is both alive and dead until we open the box and observe it. Quantum mechanics also opens up the possibility of quantum entanglement, where 2 particles can become connected in such a way that a change in one particle instantly affects the other, no matter how far apart they are. This can create the appearance of non-locality, where information seems to travel faster than the speed of light. Additionally, experiments like the double-slit experiment have shown that particles can behave like waves and interfere with themselves, creating interference patterns that are determined by probabilities. This means that the future can affect the present, because the act of measuring the particles can collapse their wave functions and determine their outcome. Field theory, which describes the interactions between particles through fields, also shows us that particles can affect each other indirectly, even across vast distances. This is known as virtual particle exchange, and it's illustrated by Feynman diagrams. The Higgs boson, for example, is a particle that is responsible for giving other particles mass. Its existence was predicted by field theory, and it was discovered in 2012 at the Large Hadron Collider. Additionally, the interactions between particles can create feedback loops that influence each other over time. These feedback loops are the result of the virtual particle exchange that occurs between particles, and they can create complex, emergent phenomena that are difficult to predict. But how does all of this relate to the possibility of the future impacting the present? The probabilistic nature of quantum mechanics means that the future is not predetermined, and the act of observing particles can collapse their wave functions and determine their outcome. This means that the present can be influenced by events that haven't happened yet, because the outcome of those events can be determined by the act of measurement. The wave function collapse is described by the Schrödinger equation, which is one of the most fundamental equations in quantum mechanics. The Schrödinger equation describes how the wave function of a particle changes over time in response to its environment. The equation is given by I times h bar times partial derivative of psi with respect to t equals h times psi, where h bar is the reduced Planck constant, t is time, psi is the wave function of the particle, and h is the Hamiltonian, which describes the energy of the particle. The wave function contains all the information about the particle's properties, such as position and momentum. When a particle is measured, the act of measurement causes the wave function to collapse to a single definite state. This is known as the collapse of the wave function. The act of measurement is described by the Born rule, which gives the probability of measuring a particle in a particular state. The collapse of the wave function has been the subject of much debate in the field of quantum mechanics, and it remains one of the most puzzling aspects of the theory. The collapse is usually seen as a fundamental aspect of the universe, and it suggests that the act of measurement plays a crucial role in the behavior of particles. The study of quantum mechanics and field theory has led to some of the most profound discoveries in physics, and it continues to be an area of intense research and debate. While the idea of the future impacting the present may seem strange and counterintuitive, it's a possibility that is supported by the laws of physics. While physicists have been exploring the mathematical and theoretical aspects of causality and time, psychologists have been investigating the psychological effects of the future on the present. Carl Jung, a famous psychiatrist, believed in the concept of synchronicity, where events that are meaningful to the observer happen at the same time, even if they seem to have no causal relationship. He believed that the future could impact the present through the collective unconscious, a shared repository of archetypal knowledge and symbols that exists beyond individual consciousness. To understand how the future can shape the present, we must delve into the workings of the human mind. Our brains use information from the past and present to create expectations about the future. This process is known as the self-fulfilling prophecy. Self-fulfilling prophecy is a fascinating concept that showcases the power of our beliefs and expectations in shaping our reality. When we have a positive or negative expectation about the future, it can influence our thoughts, behaviors, and actions, leading to outcomes that align with our expectations. For example, if you expect a job interview to go poorly, you might show up unprepared and give subpar answers, ultimately leading to a negative outcome. On the other hand, if you have a positive expectation about the interview, you might put in extra effort to prepare and perform well, resulting in a successful outcome. This concept highlights the importance of our mindset and how it can shape our experiences. By having positive expectations and beliefs about the future, we can increase our chances of creating a reality that aligns with our goals and aspirations. Moreover, the self-fulfilling prophecy also sheds light on how our expectations about the future can have a ripple effect and shape the present, influencing not only our own experiences, but also the experiences of those around us. The self-fulfilling prophecy is a powerful tool for shaping our future and offers a glimpse into the intricate workings of the human mind and the role it plays in shaping our experiences. By harnessing the power of our beliefs and expectations, we can create a future that is more in line with our hopes and dreams and shape the present in a positive and impactful way. Take athletes, for example. They visualize their future success, and that visualization drives their training and preparation. They believe they will win, and that belief shapes their behavior, which leads to their eventual success. The same is true in the stock market. Investors make decisions based on their expectations of future events. These expectations shape the present, affecting stock prices and the economy as a whole. Visualization is a powerful tool for shaping our future. By visualizing a positive outcome, we can shape our behavior in the present to align with that future outcome. Whether it's in sports, business, or personal relationships, visualization can be applied in any aspect of life. It's a tool that allows us to shape our future by shaping our behavior in the present. In conclusion, the idea that the future can impact the present and past is a fascinating concept that has been explored in psychology, neuroscience, and physics. From the theories of special and general relativity to quantum mechanics, string theory, and time travel, we have seen that time is not absolute and that events in the future can have an impact on the past. While these ideas are still the subject of much debate and speculation, They have the power to change the way we understand the world and the nature of time itself. So the next time you look at a clock, remember that time is a relative concept, and that the future may be influencing the present and the past in ways we can't even imagine. In conclusion, the future can indeed impact the present through the laws of relativity, string theory, quantum mechanics, and field theory. Physicists have been exploring the theoretical and mathematical foundations of this idea, while psychologists have been investigating the psychological and philosophical implications of it. While we may not yet fully understand the nature of causality and time, we can continue to explore these fascinating topics and deepen our understanding of the universe we live in. So, whether it's the laws of physics or the workings of the mind, the future has the power to shape the present. It's a fascinating concept that continues to captivate scientists, philosophers, and ordinary people alike. Stay tuned for more mind-blowing concepts and theories, only on our channel. If you enjoyed the video, please hit the like button and consider subscribing to our channel, 2D Time, for more programs on all things time. We appreciate your support, and let us know in comments section if there's any topic related to time you'd like us to cover, or if you have any questions. Your feedback means the world to us. See you again soon. Thanks for watching.